Log on, tune in, find out. Another good idea from Cambridge.
Formation in a two-stage adaptive optimal design, which Nancy will present to us. And as you can see, she represents University of Missouri. So, please.
Thank you, Masha. So I'm pleased to be here. I have two apologies. The first is to those of you who've seen an earlier version of this talk. And the second is the number of formulae. But my only caveat is that someone, my invitation to speak comes from people who knew both of those deficiencies in the talk and invited me anyway. So I hope that you find it of interest. I have seen two-stage adaptive design presentations in environmental contexts, where they do a large first sample and then use the information that they've got to really improve their estimates. And I've been really quite blown away by how well this approach works in that context. The clinical trial situation is kind of the inverse, in that one wants to do a small first step, and because one typically is first stage, because one is concerned about potential toxicities or other risks at putting patients in a new position. And so then the goal is to take information from a small sample and then design a efficient study. And so it's that context that motivated this work. It was the topic was suggested by Valeri, and I'm sorry he's not here. And there's been some work that is from my doctoral students in here. So two sort of motivating questions, and that is how does the selection of the treatments affect the properties of estimators? And then the second one, it has to do with the relationship between the design and the experiment. And we're used to hearing, particularly from the Bayesian community, the design is ancillary, the design is ancillary. And I, even myself, have papers where I say the design is ancillary and we throw away some part of the likelihood. And so the question is, my interest was to look at that more closely and see whether that could be justified, particularly after coming back over the comment that ancillarity does not necessarily equal independence. So we're going to look at those questions. So first, this is done in the context of adaptive optimal designs, and they have a very nice motivation. And the idea is that, for the optimal design, you've seen a little bit about that, and you've got some criterion functions such as minimize the variance of the best dose. And I'm looking in the case of nonlinear response functions because that's where I'm interested. So the designs are functions of the unknown parameters, and they have to be estimated. And the heuristics go that if your maximum likelihood estimates are consistent, then for large samples, the optimal designs will also be consistent, because they're just functions of the maximum likelihood estimates. And so as you continue making stages, you will have increasingly better estimates of the parameters that give you better estimates of the design, and your design then for each stage will be more and more and more efficient, and that this is a good, sort of heuristic justification for proceeding in this fashion. I have a proposal from Box and Hunter in 63, and if someone knows of an earlier reference, I'd be interested. So here's the basic outline. I'm taking a very simple model because it can't be simple enough. So we'll look at a one-parameter regression model, and the mean will be exponential. And so I'm kind of going to review the information theory for independent observations, so that gives us our notation and also provides a way to contrast what happens with the adaptive in the adaptive problem from what happens with independent observations, introduce the two-stage design and what happens there, and then I have some illustrations. So here's the notation. It's pretty standard, but I'll go through it because it's a lot. So we have treatments. If they were independent, we'll talk about them sequentially as stages, xi. We only take 2 because, again, I want to keep it simple. We have our total sample size being the sum of the individual samples. The weights are the proportion of subjects on each sample, which add to 1. The design is the combination of weights and treatment points. And I'll take n to be fixed, the total sample size. And then our responses for each treatment or for each stage, we have a collection of responses. And the expected value for these responses is a function eta that depends on the design point and the unknown parameter. And this is just the mean for the stage-specific mean is y bar, yi bar. So here's our model. We have y has expectation eta plus an error. The error is normal 0, 1. I'm going to look at the specific case where eta is exponential, and again, we observe our responses at each stage. So now think IID for a moment. This is the likelihood, the product of the two individual densities for each stage, and it's nice and normal, so we write this as proportional to the normal kernel here. And I now rewrite this in the form of the canonical exponential family, because a lot of the properties that we attribute to maximum likelihood estimates go hand in hand with the random variable being from an exponential family. And I'll contrast this later. So just rewriting this exponent here, we can write the likelihood is proportional to, we have a parameter times a statistic, that's key in the canonical representation, and then the other term is just a function of the parameters and not the data. And I emphasize that because when we get to doing this for non-independent random variables, the second stage design point will be a function of the data. So one thing to anticipate is that we're not going to have an exponential family anymore. So in my example, there's some probability that that estimates are going to be on boundaries, but those boundaries go to 0, and I don't want to make the slides too cluttered, so I'm just going to ignore them. They are not important to the points that I want to make. So I'll just be talking about the interior of the dose response space. Okay, so this is what I mean by a lot of mathematics here, but bear with me. We have the single unit score function, Sij, j subject, ith stage. And I emphasize that it depends on your responses. Given the treatment, it's the derivative of the log of the density. This is the general form for the normal model that I wrote down, and this is the specific form once we've assumed an exponential response mean. So within stages, we need to sum these up to get a stage-specific score, and then we need a total score, which is the sum over the stages. What is used in decision-making in sequential optimal designs is based on this expected unit information. Again, for one subject, I use the notation mu I, and it's this is a function of the design point and the parameter. It's the conditional variance of the observations given the data. It's the conditional variance of the score function, where the conditioning is given the design point. And I just remind you that that's minus the second derivative of the log likelihood. Here it is written out explicitly for the linear model to remind you that if you were going to use the observed information to estimate the information, you would be plugging estimates of the information into this term. Once we take the expectation, the second term goes away, and we're left in the exponential case with xi squared, eta I squared. I'm not going to say much about observed information here, but there is a substantial literature that would suggest that for small samples, if one is going to, for analyzing the data, the observed information better reflects the variation in the data than the expected one does. So that's something to consider further. We then have the average expected information, which is averaging the total variance of the score function, which is just the weighted sum of the unit informations weighted by the proportion of subjects at each treatment. Okay, so the information is only important as it relates to the variance of the parameter estimates. So that's where I'm going here. We have to get the relationship between the variance the variance of the score function and the variance of the parameter estimates. And so we have these standard sort of set of conditions. The log of the likelihood needs to be differentiable where the true parameter is. Take a Taylor series expansion, we get a formula. The maximum of, so we want to know where the maximum of the likelihood is, which will be where the maximum of the log likelihood is, and we can simplify that that criteria to be where this equality holds. So taking the derivative of the log likelihood and just rearranging the terms in the neighborhood of the true value, we get this formula. So this is giving us the relationship between the parameter estimate we're interested in and these score functions. And typically, what we have here is a random variable which by the central limit theorem is going to go to normality. And over here, minus the second derivative of the log likelihood, we have a random variable which will go in probability to the information matrix. And that's the first place the information matrix comes into the relationship. Consider the numerator and the denominator of those two expressions separately. So what we have here is we have the term just involving s, and we have the term involving the derivative of s. So just look at those two terms separately. Because we have a normal model, S is got a normal distribution, and the variance is the weighted sum of the information, the unit informations. In the denominator, we have the average of the second derivatives of the score function. Again, we have a weighted sum of two sample averages, and the law of large numbers gives us the weighted sum of the information matrix. We're still talking in the IID case. And then Slutsky's theorem, which requires that this thing we have in the denominator go to a constant, Slutsky's theorem allows us to put those two pieces together and get the result that that we have a normal random variable with variance the inverse of the information matrix. Okay, that's the review. Now, what are we doing with adaptive designs? Optimal adaptive designs. Okay, so observe you fix x1. So the x1's given to you, or you get it from somewhere. You get your observations, and now we're going to select the stage 2 design point. And here we're going to do that to maximize the variance in the observations at the second stage. And we have to estimate this because it's a function of the unknown parameters. We're in a nonlinear model. And so what do we have to estimate it with? It's the maximum likelihood estimate at the first stage. So we can, for this model, we can actually calculate what the maximum likelihood estimate for the first stage is. And so we plug that in, and we have, well, I guess here it's still in terms of theta 1 hat, but you can plug it in. If you plug this in, you have x2 written as a function of, what is it, y1 bar. So the point that you're going to use in the second stage is a function of the sufficient statistic from stage 1, y1 bar. Okay, so now let's go back to the likelihood. For the adaptive case, the only assumption we make is that given the treatments, the responses given the treatment are independent of the past. So in particular, the second stage responses do not depend on x1 if you know x2, and they don't depend on y1 if you know x2. So here's the likelihood, which is taken just by successive conditioning. We have all of these components. We take y2 given everything else, and it reduces, given everything else, this would be the first term, which reduces to this one. We have the stage 2 design given what's left, and then we have the y1 responses, the stage 1 responses given x1. So we have to look at this term in the middle. And for sequential optimal design and a number of other procedures, but not adaptive procedures, but not all of them, x2 is completely determined by x1, and y1 it is deterministic. And so this will be a delta function. And in fact, the design is ancillary, and we can write the likelihood as the familiar product between the two densities. That is the way we commonly write it. So most people would stop there and say everything's fine, you know, everything's fine. So let's look at it a little more carefully, though. We're going to write this out. We have the normal expression, the normal kernel from the first stage, and nothing's changed here. We have a parameter times a statistic, and then we have a parameter in the next term. We get to the second stage, and now things are different. We have a nonlinear function, and I should stick the thetas in here to make it explicit. So we have a nonlinear function of the stage 1 data and our stage 1 response times the stage 2 response. And then over here, this is not just a function of the parameters anymore. This is a function of the parameters and the data. So we have lost this. We no longer have an exponential family, because exponential family requires that you have a product of data, a function of the data times a function of the parameters. Not that they're all mixed up like this. Now you can see what it'll take to make an exponential family out of this just by looking at this term, or these terms here. That is, if you have a very large sample, stage 1 sample size, then y bar 1 is going to go to its mean, and therefore it'll be constant. And as soon as y1 goes to a constant, now you're back with a function of the parameters times a function of the data and a function of the parameters. So if you have a very large stage 1 sample size, then you don't have to worry about what the consequences of not having an exponential family might be. But if you have a very small sample size, stage 1 sample size, you do. Okay, so here's looking at the information a little more carefully. We have the expected value of minus the second derivative of the log likelihood, and I write, this was on the other slide, I write it out so that you get all the terms in the middle. This is for our particular example once you take the expectation, and I had defined that to be mu sub I. So let's look at the second stage and see what's happened here. So I just plug in what eta I is here, and now actually I should have evaluated at y1 hat right here, because what I do here is plug in y1 hat. And I do that to make it explicit to you that this second stage information is a random variable. It is a function of y1 bar. So in most applications that I've seen, it's taken to be fixed, a fixed point, a constant, and it's not. It's a random variable, has its own distribution. And so if we look at okay, this, let's see, what have I got here? That should probably be a capital, well, it doesn't matter. Anyway, so the unit information from stage 1 will be just what we had before. But the unit information from stage 2, what I'll call the unit information, you have to wonder now what it is this, so Fisher's information. To get Fisher's information, you have to take an expectation of this over y1 bar. Okay, that's what I wanted to say. Sorry, it took me a little bit to get there. So this thing, which is used in practice as if it were Fisher's information, is not. To get Fisher's information, one needs to take the second expectation. And that makes things more complicated if one wants to use Fisher's information as opposed to something. So here this sort of repeats the points. The second stage, quote, information is a random function of y1 bar. It only will converge to a constant as the stage 1 sample sizes converge to infinity. And the other thing to observe there is, you think, okay, well, I'm going to condition on my x1 and my x2. I mean, let's just be realistic here. We condition on our data points. So what are we talking about if we say we're going to condition on x2? Well, x2 is a one-to-one transformation of y1 bar. So if you say you're going to condition on x2, you really are or should be you're conditioning on all your stage 1 responses. I mean, that's what that means. And so is that what you want to do? So now here's this formula we had again that relates the parameter estimate with the score functions. And so we've got in our score, what we have now is a function of wherever it is. We have a function of S and y1 bar. So if we want the density of S, then we've got these two statistics. And one way to look at that would be by conditioning, to condition S on y1 bar and then integrate out S. And if you think about doing that, here's S, which would be the numerator. If we condition on S, then the first term is constant, condition on y1 bar. The first term is constant and the second term is normal. Well, this is constant, so you could bring that inside, but I left it out here for the moment. And the second term then is still this linear combination of score functions. And I put this asymptotic result in here, which is true if n goes to infinity, but if you have a small stage 1 sample size, it is not true. And I have a student working out the various combinations of n1 goes to infinity and to different ways that you might be taking limits or not taking limits. And so there's details you don't want to see here about that. Now I have just a few minutes for an illustration. So take theta equal to 1, and we have a range for our dose space. So our initial treatment is 0.5. If we took if we maximize the variance and evaluate it at theta equals 1, the best place we can put our second design point is at the point 1. And of course, our adaptive algorithm puts that point at theta 1 hat instead. So try to read this thing. I'll tell you what this is. Okay, so the top line going across the top is Fisher's information if you treated everybody at x equals 1. So x equals 1 is the best place to treat people, and so this is the best you can do. The other straight line down here is Fisher's information if you treated at x equals 0.5, which I'm going to say is our starting point. So this is the best you could do if you treated, if you guessed wrong, you didn't start at the you didn't treat at the optimal spot, but you put everybody at 0.5. And this line going across here is the linear combination of x1 and x2, where the x-axis is the weight on stage 1. So given you have some linear combination of weights, given you have some combination of subjects on stage 1 and stage 2, this line tells you the best thing you could do under those circumstances. The three kind of wiggly lines, which I haven't figured out how to get smooth yet, maybe the not enough simulations, or so these three reflect three different sample sizes now where we're doing the adaptive design. So we have a really small adaptive design where you almost have no patients on stage 1 if you use that, 100 and 300. So the small sample doesn't do very well at all. The size 100, and these are random variables, so this is an expected information matrix, or information value that I'm giving you. The second size, by about 0.4, that is 40% of the subjects on stage 1, will be doing about as well as if you just put everybody on stage 1 and somehow been able to do the best you could, and been able to do the best you could. This is n equals 300, and it's getting close to the optimal design line. I'll show you a larger sample size on the next slide. So this is now, remember I said those are random variables, so now I took just, this is our linear combination of, this is Fisher's information, locally optimal for the linear combination of weights. And what I have now is n equals 1,000, but I have quantiles. So the top here is the 75th percentile, and the bottom is the 25th percentile on the information measure, which is not getting up to Fisher's until about 0.6 on average. And you can see it goes both sides, emphasizing again that this is a random variable. Now, I'm not really sure how to interpret this. I mean, I don't know whether, how to interpret Fisher's information. If one got a point on this line, are you reporting a information that's bigger than it really is, or are you, or if you use Fisher's information as the true value of information, are you underreporting what the variance is? Maybe both of those can be true. I think I can stop. I have one more, but I'll just show you this. This is n equals 30, n equals 100. The weights are 0.5, and it's to show you the distribution of mu2. So we have 2.5th percentile, 97.5 percentile. They're as far apart as you can be, and this is the median. 1 again is the optimal design point. This is stage 1 design point. So the median is very close. So if you're at the right place, the median is very close to Fisher. If you go to say it's 100, what's interesting to me is this bottom, the lower percentile comes really up, so that the whole distribution of these information measures gets pushed from the bottom up to the Fisher information line. And that's all I know. Thank you.
Well, thank you very much. If you have any questions, please ask. If you have comments, please make them. Ben?
Just clarification. your designs are one-point designs, X1 and X2, because it's a one-parameter
Right.
model.
So which phase you think that would be the most appropriate procedure in clinical trials? Phase 3 or phase 2? I didn't quite get that.
Well, this is trying to get at the basic idea of what information, I mean, okay, so, Valeri's the one that does the adaptive optimal designs that I know of in clinical trials a lot. And he does them in phase 1, 2. But a lot of, and so we're looking at the sort of the foundational theory that underlies that is to, okay, so if you're so Valeri's worked in cardiovascular disease. In cardiovascular disease, they have large sample sizes. He won't think, it's common for him to thinking of doing an initial sample size of 100 or more, 400, because he's thinking of total sample sizes in the thousands.
So that would be like often phase 3 rather than...
Well, but for him, it's early phase.
Yes.
Now,
Early
if you're coming from a cancer clinical trial environment, you're in the really small sample size situation.
That's right.
And so a lot of this is then much more critical. What I just showed with n equals 30 is that, probably for n equals 30, nothing that you do is going to be very good, and that needs to be recognized more
Yes,
clearly.
but it's not only the matter of sample size, but also how many initial doses, or perhaps how many candidate doses you want to look at.
Well, yes, you just add complexity to this problem.
That's right.
I mean, here we just went from, if you think of it as a dose response thing, you just did 2 doses. And you would want to do more doses than that. But the question of how do we interpret this this thing we've been calling the information, I mean, that's what I was trying to get at. And so that was one point, and the other point is that it's a random variable, and we're not evaluating or reporting it as a random variable. We're evaluating it as a fixed point. And so so I think that is we just need to be clear in our minds that that's a random variable.
And first, lots of them. Sorry, please.
Nancy, it's good. Wonderful talk. I love it very much. The only concern I might have is you make assumption about the independence, about the new treatment is independent with the previous in some way. How robust is the procedure if that's violated somehow?
It's true in every example I've known. I mean that we think of if I give you a treatment, it doesn't depend on what I gave Joe yesterday. Now, if you're talking about treatments within subjects,
Right.
It would be totally violated, and I think that's an interesting problem. But if you're talking about independent subjects, it's not a big assumption.
I think that will be last question. Yes, please.
Sort of the standard wisdom would be that working sequentially would improve things. But in your designs, they really don't seem to be improving things very much, and maybe even making things worse. Is there any sense as to whether this is because you're not getting good estimation from the first stage, or is it largely because of the added variability that you look at from looking at the extra variability of where you hit on the second stage?
Well, I think those are combined. I mean, I think where you hit on the second stage is highly variable if you don't get good information at the first stage. And so from this and other things that I've looked at, it's not uncommon that introducing a random rule, which seems to be very smart and very clever, can induce enough randomness that the benefit is lost. And I think that's very common in many of the designs that have been proposed that are adaptive designs, and needs to be part of the evaluation criteria.
Okay, thank you very much.